Hello everyone. Today we are looking at another Leetcode problem. This is 494 target sum. So in this problem, we're given an integer array nums and an integer value target, and we have to build an expression out of nums by adding a symbol which can be either plus or minus before each integer. And we have to return the number of different expressions that can build the target value. So let's take an example and understand this. Let's say my example nums has 5 ones and my target is equal to 3. Now what I can do is I can either attach a plus or a negative in front of each element. So what that means is I can have, let's say, -1 and then +1 +1 +1 +1, which gives me +4 here and -1 here, giving me a total of 3. And this way I can just alternate these symbols and get multiple variations, right? So you can understand, let's say 3 ones are here. Okay, so I got like 3 positives and 1 positive and then -1 here, overall giving me 3 again. Now this is what we need to do. Let's think about it from the recursion point of view, right? Because it's quite evident that we have to create all possible variations. And so now let's think of it as a recursion problem. So let's say let's write our array once again here. So this is an array. This is our nums. And so we are starting at index equal to 0, and our current sum is also equal to 0. We haven't really taken anything. Now there are two ways I can take this, right? I can either associate a plus or I can associate a negative sign to it. So when I associate a positive sign, I then go to the next index, so it becomes 1, and the sum now becomes equal to +1. Likewise, this becomes -1. Now again I have two possibilities, right? Plus and negative. So I get f of 2 and then 2 here, and then I get to 2. So +1 -1 makes it 0. Same way, let's take plus sign, positive and negative. So I can go to 2. So adding +1 to -1 gives me 0, and adding a -1 to a -1 gives me -2. So I'm not going to proceed further. I hope you get the drill here. But one of the things to note here is that we are already starting to see subproblems that repeat. So this can be solved using DP approach. So let's quickly look at the code for the recursion. Then we'll also solve the tabulation, and then between the recursion and the tabulation we'll do a trade-off. So let's look at the recursion code here. Maybe let's have this view of the recursion on the screen. Okay, so let's say my recursion code is called recurrence, which takes index, which takes current sum, and it will also take DP, because we can clearly see that there are repeating problems. Okay, so if index comma current sum in DP, we can return DP of index comma current sum. Okay, also if index happens to be greater than or equal to len of nums, which means if we were at the last index and then we've gone beyond, then this is the time that we check if the sum that we got so far is actually the target sum because we cannot generate any other sum from it. So this is the point that we evaluate. So we will return 1 here if my current sum happen to be target, else I would return 0. Now, once our base cases are done, let's now look at the branching condition, the positive and the negative branching conditions. Alright, so my positive branch says I'm going to go to my recurrence function with the next index, and the current sum will be incremented by the current index value. Okay, and then you pass dp as it is. Same way, my negative branch is equal to recurrence index plus 1 current sum minus nums of index. So this can be also written as plus minus 1 times this comma dp. And finally, my dp of the current index comma current sum is nothing but positive branch plus negative branch. And why is this the case? Because as we keep progressing, we are going to, at some point of time, we are going to get n, which is like the length of the array, comma, the target value. Okay, and if you see, each of the path that was taken to get to this value will be different. And so what we want to do is count the number of paths that we have seen. And so if we want to count the number of paths that we have seen, let's return 1 from here. When we return 1 from here and sum up all of the returns that were 1, then we are basically summing up all of the unique paths that got me to the end of the array with the sum equal to target. So that's what we are trying to do here. And then finally we can return this value. Okay, this is the recursion approach. Okay, now let's quickly think about the time complexity, right? So we have n elements. Okay, before we use dp, so this is without any memoization, without using the dp itself, each element gives me two options. Okay, either plus or negative. So the total number of possibilities that I would have to compare without using dp, without reusing the repeated verb, would be order of 2 power n. Now let's look at what is the time complexity with dp. So that would be equivalent to how much compute is required to form the dp. So let's analyze our dp, right? So our dp is formed of two factors. One is the index, other one is the current sum. Okay, this index ranges from 0 to n minus 1. So the number of elements here are n. And if you look at the current sum, I can have all of the elements which are negative. So I will have min sum, which is equal to minus 1 times the positive sum of everything. So let's call it S. Starting from 1 going up to S, this ranges, and then we also have a 0 in between. So totally we have 2 times S plus 1 element. So the overall time complexity for with dp solution is order of n times 2 S, you can say, which is order of n times S. Alright, so now that we understand the range and state of index, So it is greater than the index of the array, but this is where we are checking. So you will now have on the x-axis, you will have the sum. So starting from 0 on left and right side, you will go up to minus s, and on this side you will go up to positive s. And let's say your target happens to be somewhere here. So what we will do is for dp of n, if the value of the sum is equal to target, then we return 1. At rest all of the places we will return 0. That's our initial configuration. Alright, so this is our DP, and now let's start to fill this up. Let's also have all of the other places initialized as 0 because they will get overridden. 0 is fine here. Okay, now let's write the pseudocode. Okay, let's have a def target sum function which takes nums as a list of integers. We have target of type integer, and what we have to give is the number of distinct ways to form the target, so that's also an integer here. Alright, so n now is len of nums. Max sum is my sum of nums. Min sum is my... Okay, now let me create dp, which is a 2D array, and we initialize by default with 0. 0 for dash in range of min sum to max sum plus 1. Okay, so this is the column range that we have. Now let's work on the rows. For dash in range of n plus 1. Now we are taking n as well because that is the terminal state. Alright, another important point to note here is if we realize after calculating the max sum that the target is greater than max sum, then we can never create this. So let's return 0 ways to achieve target as a sum. Now otherwise what we should do is fill this in as the initial state. So dp of n of target equal to 1. But there is a catch here. The catch is that I can have negative values as well. Now the problem with the negative value is that when I use this negative value here as -1, -2, it's gonna give me reverse indexing and not these values that I want. So I'll have to create an offset for it. Okay, and the offset is nothing but max sum. Okay, so this is done. Now let's start to fill up the DP array. For index in range n minus 1, minus 1, minus 1. We're not going to be filling nth state because nth state of index. That's because that is a terminal state. We already know the values for that. For anything other than target, we are going to return 0. And only for the target, we are going to return 1. Let's proceed for current sum in range of min sum, comma max sum plus 1. My positive value is current sum plus nums of index. Alright, so for this value that I received by adding positive symbol, let's see what the output of the recursion or the output for this particular call is going to be. I'm going to call it positive branch, which is nothing but dp of index plus 1 times offset, which is max sum, plus the value that I have received from the positive symbol. Okay, now this is the output. Now this is possible when this value in the second index is actually within the range. So let's add that condition also. So this is the output if my positive value happens to be lesser than or equal to max sum, else 0, which means it's gone out of bound, and that time I'm going to return 0. Let's do the same for the negative symbol. So negative value is equal to current sum plus minus 1 into nums of index, and my negative branch is now equal to dp of index plus 1. Let's add the offset max sum plus the negative value. Now again, this value is possible to get if this sum is within the range. Okay, so let's add that condition. If my negative value is greater than or equal to min sum, else 0. Okay, and finally dp of index at cursum is nothing but the summation of the values that I got from positive branch plus the negative branch. Okay, and with this I would have filled up all of these values, okay, including the things here. But what we want here is this particular value, which is starting at index 0 and the current sum is 0. So this is the value that I am interested in. So let's return that one. But remember, again, we will have to offset it with the max sum because this is at in the middle and not at 0th index. So finally, after all of that is done, you can return dp of 0, 0th index, and at the offset max sum plus 0 is just max sum. So this is what you're returning. Now you can do an optimization in this technique as well. So if you look at this array, when you're solving n minus 1, you're only using n. So let's look at this place, right? When we are at n minus 1, we only look at index plus 1. So for every index, you're only looking at one index ahead. So which means when I'm trying to fill index plus 1, I don't need any of the things above. I just need the index right after it. Right? So that can be our optimization where we say that we don't initialize the whole TP matrix. We just, so let's call this the optimization. Okay, where what we are saying is that our DP is not the whole table, but just one vector, but just one array. So you get 0 for dash in range of min sum to max sum plus 1. That's all. Okay, and you'll say that dp of now max sum plus the target is equal to 1. That's all. After that, when you're doing the for loop for index for cursum, here for every index you will initialize a new dp, okay, which is going to be of the same range as this. So range of min sum to max sum plus 1. Alright, and you will do everything the same way. So you will say my negative value is equal to, instead of saying index plus 1, you will directly fetch the you'll directly fetch the column. So you will say this is nothing but my max sum plus my we can call this the negative branch, and we can say plus the negative value. Yes, we call it value, negative value. And then you can have your else conditions, your else, same way. So what we've done is we have gotten rid of one dimension, the index dimension, from here. So our time complexity for this is still order of n times s, but our space complexity, which was earlier n times s as well, which was number of index into 2s, the number of columns plus 1, has now reduced to just 2s plus 1, because we are not maintaining all of the rows, we are just using one additional row at a time. So my new time complexity is nothing but 2s plus 1, which I can write it as order of s. Now there is a very important point to talk about here, where in this particular case our dp solution is less efficient than my recursion solution. Okay, and to tell you what this means in numbers, my recursion solution ran in about 200 milliseconds and dp solution was running in 300 milliseconds, even though their overall time complexity, if we calculate, which is a rough calculation, is the same. So order of n times 2s plus 1 and order of n times 2s plus 1. Okay, and so you may ask, why is this so? The reason for that is the recursion in this particular case gives me a sparse calculation as compared to the dp. Let's try to understand why is that the case. Okay, so when we do recursion, I start with f of 0, the index, comma 0, the current sum value, and then I add plus 1 and I add minus 1. So it becomes this value. So at f of 1 comma 1, 1 comma minus 1, and so on. So we will go on to compute like this, and we will reach this particular value, which is nothing but the state, not the nodes of the recursion, which is at n comma target. We will reach this x times. Okay, so that's what we're counting through the different paths. I'm trying to simulate the recursion within the tabulation to help you understand the difference in terms of the sparsity that we are having right now with recursion. So now what happens is at index equal to 0, when I have not picked up anything, it is not possible for me to get any of these other states, but we still compute it. Likewise, in the next state, I can only go to two other possible values by adding just two of these symbols. Okay, but what happens is that we still compute all of these states which are not relevant, and because of this reason, because of this sparsity in this particular problem, our recursion will do better than our dp tabulation. This is dp tabulation. Yes. So that's about it from me this time. I'll see you again with another problem next time. Thank you. Bye bye.